All right, I'm really happy to be here at JuliaCon. I know how much work it is to organize a conference, so thanks to everyone who did all the work to cause this to happen. And thanks especially to all of you who were conscientious enough and curious enough to show up to a conference about a pre-1.0 language. So my name's Lindsey Kuper, and I'm a research scientist at Intel Labs, as Jihao mentioned. And this talk is a tour of ParallelAccelerator.jl, which is a library and compiler for high-level, high-performance scientific computing in Julia. And this is one piece of a project at Intel Labs that we call high-performance scripting, and it's the work of many people whose names I've listed here. So a couple of months ago, I wrote a guest post for the Julia blog introducing the Parallel Accelerator package. So thanks to Viral and Stefan and others on the Julia team who gave us the opportunity to do that. And so I was thinking, well, this talk will be really easy to give because I can just regurgitate the things that I already said in the blog post. But as it turns out, I have more that I want to talk about. In particular, I want to introduce you to my friend Laura. So this is Laura, and she's a geophysicist who studies the physics behind ice-penetrating radar. So her research group collects radar data by flying a plane like this one over Antarctica, transmitting radar pulses and listening for and recording the results, which appear in radargrams like this one. And by studying the radar profile, they can learn more about the ice and the rocks underneath. And right now, she's working on trying to develop signal processing techniques that will allow them to discriminate between echoes originating below the aircraft and off to the side. So the mathematical tools in her toolbox for doing these kinds of things include convolutions, FFTs, matrix multiplication, and so on. She's an expert in those things, and they are what she wants to be thinking about when she writes code. She hates doing manual memory management, and she doesn't know how to schedule parallel tasks across compute resources, or even if she did, she still wouldn't want to have to worry about it when she could be thinking about this. So she prefers to use a programming language that frees her from having to think about those things, at least when at the prototyping stage. And in other words, she wants what I'll call a productivity language, which is a language that will enable her to get stuff done at a level of abstraction that matches her expertise. So Laura and her colleagues and others like them typically use a language like MATLAB or Python or R or Julia. And these languages give you a high-level programming model, and they generally don't make you think about things like memory management or thread scheduling, and they typically come with an extensive set of libraries for doing the kinds of things that you might want to do, like matrix multiplication or FFTs. But once you have written a working prototype in one of these languages, there's a dilemma that arises when you want to scale up your code to run on a larger input size or for more iterations or at a finer granularity. And the productivity language that you're using turns out to be too slow. So now what do you do? Well, the usual approach is that you have to port the code from the productivity language to what I'll call an efficiency language like C or C++. Or more likely, you enlist the help of somebody else to do that for you. And in fact, maybe some of you have been that unfortunate grad student who was brought on to do this for somebody's project. And this takes considerable time and effort, and doing it right requires expertise in the efficiency language, plus probably expertise in high-performance computing tools like MPI. And you end up with code that is indeed much faster and more efficient than the original, but it's also more brittle, harder to experiment with, harder to maintain. Plus, you're likely to introduce bugs at this stage too. So is there any way around this trade-off between productivity and efficiency? So it turns out there is a well-regarded way to avoid this productivity versus performance dilemma, and it's using high-performance domain-specific languages, or DSLs. So quite often these DSLs are embedded in a general-purpose language, so we'll speak of embedded DSLs or eDSLs. And a few examples are the languages developed using the Delight framework from Stanford for building eDSLs in Scala. And then there's the CJITS project at Berkeley, which is similar, and that's a framework for developing high-performance DSLs embedded in Python. And there are others as well. So I really like this three-way trade-off that the Delight team at Stanford formulated between generality, productivity, and performance. So in other words, they say by using DSLs, we give up generality to get productivity and performance. And the idea is that the combination of all three is this magical unicorn that doesn't exist. So what the Delight people found is that by restricting things to a particular domain, you can offer both a high-level programming model and high performance. And the reason for that is that domain specificity allows the compiler to make smarter optimization choices. But if these embedded DSLs for scientific computing are so great, then why are they not more widely used? So we think that there are a couple of problems that hinder adoption. And for one of them, of course, is the learning curve. So computational scientist programmers are likely already familiar with a general purpose productivity language for scientific computing, like MATLAB or R, Julia, etc. And they already have a body of code written in that language. So learning an EDSL and porting code to it, although it's not necessarily as painful as porting directly to the efficiency language, it's still a burden. And it's also hard for even the most well-designed EDSL to anticipate all the use cases that the programmer is eventually going to encounter. And then there's what I call the rest of the productivity story. So in this trade-off that I talked about before, by productivity, they mean offering the right high-level abstractions that you need to work at the level of your expertise. But what we find is that there are several other dimensions to productivity in an EDSL beyond just this question of whether it offers the right high-level language abstractions. So in order to be a useful replacement for a general-purpose productivity language, an EDSL has to have fast compilation time. Maybe this isn't an issue all the time, but if you're used to working in the REPL, then it is. It needs to be robust. That is, the compiler has to be able to handle, if not optimize, a wide variety of inputs that a non-expert might throw at it. And a lot of EDSLs fall down here. If the compiler encounters something that it can't deal with, then it'll just fail with an unhelpful error. Programs in the EDSL have to be reasonably debuggable, using debugging techniques that the domain programmer is already familiar with. So this is somewhat related to the previous point. EDSLs often have terrible debugging support. The error messages are really confusing because they're in terms of the host language rather than in the embedded language. And finally, the EDSL has to be available on the domain programmer's platform of choice. There are a lot of people who are using MATLAB on Windows, right? And if you give them something that's difficult or impossible to use on Windows, then they won't use it. So you could argue that none of these are open research problems, right? And I'm a researcher, so why am I looking at this? They're engineering problems. But nevertheless, they take a lot of effort to resolve, and failure to satisfy any of them is likely to hinder the adoption of a high-performance EDSL, no matter how good its performance is, and no matter how suitable its high-level abstractions are. So what can we do about this? So this talk is about our work on a system that tries to overcome these challenges. So ParallelAccelerator is a combination of a compiler and a library working together to provide high performance in a productivity language. And as with those embedded DSLs that I talked about, our starting point is an existing language, in this case Julia, which I'll say more about in a bit. But unlike existing embedded DSLs, ParallelAccelerator mostly focuses on speeding up execution of things already present in the language. So in particular, it's targeting numeric code that can be expressed with implicitly parallel array operations, things that we can think of as being map or reduce or comprehension. It's also more than just an optimizing compiler for an array language. It also supports additional domain-specific constructs, such as, for example, a run stencil construct for stencil computations. And I'll say more about that later, too. But these domain-specific constructs have two implementations in ParallelAccelerator. And this is, I think, a key point. There's a library version, and there's a high-performance native implementation in the ParallelAccelerator compiler. And it uses the same parallel execution framework as the things that are part of the Julia language. So any program that leverages ParallelAccelerator is still a valid Julia program that can be executed without our compiler turned on. And that means that it's possible to turn off the compiler and run in library-only mode during development and debugging, and then enable the compiler later on when it's time to deploy. And that is nice because it lets us conveniently sidestep, not solve necessarily, but sidestep all of those issues that I mentioned earlier that hinder adoption of high-performance embedded DSLs. So we've implemented all this as a library on top of Julia, and we released it as a package called ParallelAccelerator.jl. It's open source. We released it last October, and when I checked yesterday, it was the 11th most popular Julia package on GitHub. I was really hoping we would crack the top 10 before JuliaCon. But no, we're number 11. It's a registered package, so you can install it today with package.add. And the key part of the interface is a macro called ACC, which is short for accelerate. If you saw my colleague Essan's talk yesterday about HPAT, you already saw ACC. So you import our package, and then you can annotate functions with ACC. And doing this lets you designate the parts of your Julia program that you want to compile to optimized parallel native code. So under the hood, the ParallelAccelerator package is a compiler that is itself written in Julia. So what does Julia normally do? Well, it JIT compiles your code to LLVM. And what we do is intercept that process for functions that are annotated with ACC. And ParallelAccelerator compiles those annotated functions to C++, and then it hands them off to an external C++ compiler, which could be GCC or ICC. And then that'll compile a native library. And finally, on the Julia side, we generate a function that calls into that native library. And we replace your calls to the ACC annotated function with calls to that proxy function. I put an asterisk here on Julia to C++. And that's because we plan to stop doing that. So as you know, Julia 0.5 is coming soon, and it'll have its own native threading. And that means that we can avoid this whole process of sidestepping the usual compilation path in order to get parallelism, and we can instead target Julia's own native threads. And we're working on this now, so it'll be ready by the time 0.5 is, hopefully. So what does our compiler actually do? Well, at a high level, the idea is to identify implicit data parallel patterns like map, reduce, array comprehension, and stencil that for the most part already appear in user programs. Especially they appear if the programmer is writing code using high-level array operations, which are common in scientific computing anyway. And then we can compile those to explicit parallel for loops. And importantly, we also do some aggressive optimizations along the way so that we can avoid the runtime overhead of things like array bounds checks and allocation of intermediate arrays. So I'm going to talk a little bit more about those parallel patterns and about our compiler pipeline. But first, I want to show an example and some benchmark results. So this is an excerpt of a Julia implementation of the Black-Scholes option pricing benchmark. So we have this function, Black-Scholes, which takes several arguments, each of which is an array, potentially a very large one, depending on the problem size. So to understand this talk, you do not need to know what the Black-Scholes algorithm does. The thing to notice about this code is that the algorithm does several computations involving pointwise arithmetic on those arrays. So there's some addition, subtraction, multiplication, and division in there. And every one of these arithmetic operations here is array arithmetic. Notice that there aren't any for loops here. Instead, this code is written entirely in array style. So this code is really screaming out to be parallelized. And we hear it screams. So the other important thing to notice about this code is that there's almost nothing special about it compared to plain Julia. So it imports our library here at the top with using ParallelAccelerator. And we've used the ACC annotation on the Black-Scholes function. But other than that, this is just plain Julia code. And we're using type annotations on the argument types, which, as you know, are optional in Julia. And they're also optional when using ACC. But generally speaking, you do have to write code that's what Julia calls type stable. So here's what happens when you run it. These are performance results for Black-Scholes when each of those array arguments has 100 million elements. So the first 3 bars here coming from the left show performance results for ParallelAccelerator using different numbers of threads. This is on a 36-core machine. So with 18 threads, ParallelAccelerator runs in 0.27 seconds. With 36 threads, matching the number of cores on the machine, it drops to 0.16 seconds. And the third bar is results just running on 1 thread, which comes in at about 3 seconds. And for comparison, the rightmost bar is results for plain Julia. That is a version of the code without ACC, which runs in about 21 seconds. So I think it's interesting to note that the ParallelAccelerator implementation outperforms plain Julia by a lot, even when just running on 1 core. And the reason for this speed up is that ParallelAccelerator does more than just parallelize code, despite its name. The ParallelAccelerator compiler is able to get rid of a lot of the runtime overhead that's incurred by array bounds checks and allocation of intermediate arrays. After that, we add parallelism, and we're able to do even better. And so for this problem size, we end up getting a total speed up of more than 100x over plain Julia. So this is one example, which admittedly is in kind of a sweet spot for ParallelAccelerator to work on. So let's step back and look in general at the parallel patterns that we support. So as I mentioned, ParallelAccelerator works by identifying these implicit data parallel patterns in source code and making that parallelism explicit. And these patterns include map, reduce, array comprehension, and stencil. So map first, as we saw in the Black-Scholes example, the addition, subtraction, multiplication, and division operations that we saw there are pointwise array operations that take input arrays as arguments and produce an output array. And ParallelAccelerator can translate those into data parallel map operations. You can look at the ParallelAccelerator documentation for a list of all of the pointwise array operations that it knows how to parallelize. We also can handle array assignments and turn those into in-place map operations. So for instance, if you were to write A equals A times B, where A and B are both arrays, that will map the times over A and B, and it'll update A in place with the result. So for both standard map and this in-place map, it's possible for us to avoid any array bounds checking once we've established that the input arrays and the output arrays are the same size. Then there's reduce. So reduce operations take an array argument and they produce a scalar result by combining all the elements of the array with an associative and commutative operation. And parallel accelerator can translate certain Julia functions into data parallel reduce operations when they're called on arrays. And so I've listed those here, minimum, maximum, sum, prod, any, and all. And then array comprehension. So as you probably know, Julia supports array comprehensions, which are a handy way to construct arrays. And this is an example of an array comprehension that I stole from the Julia manual. So it takes a one-dimensional array, x, as its argument, and it constructs an output array. And here, every element in the output array is a weighted average of the corresponding element in the input array and its two neighbors. So this is a array comprehension, and these can also be parallelized by parallel accelerator. And basically what it does is it transforms these to code that first allocates an output array, and then it does an in-place map that can write to every element of the output array in parallel. And array comprehensions, it should be noted, are a little bit different from map and reduce in that they involve explicit array indexing. But it is still possible to parallelize them in Julia as long as there are no side effects in the comprehension body. And the comprehension body is everything that comes before the for. And we use a conservative static analysis to try to identify and reject side effecting operations in comprehensions. And then there's this stencil thing. So in addition to map, reduce, and comprehension, parallel accelerator targets this fourth parallel pattern. A stencil computation, if you haven't heard of it before, a stencil computation updates the elements of an array according to some fixed pattern that's called a stencil. And in fact, this average comprehension example above could also be thought of as a stencil computation because it's updating the contents of an array based on each element's neighbors. But stencil computations differ from the other patterns that we support because there's not actually any built-in user-facing language feature in Julia that's specific to expressing stencil computations. So we added one. So we introduced a new user-facing language construct called runStencil for expressing stencil computations in Julia. So next, we'll look at an example of how that works. So in the previous code that I showed you, it was a parallel accelerator program that was basically identical to the plain Julia version, except for importing the parallel accelerator library and using the ACC macro annotation. But this example is a little different because here we're using runStencil as well. So as I said, a stencil computation involves an array of some kind, and you want to update each element in the array based on the surrounding elements. And a good example of that is the Gaussian blur computation, where you want to blur an image. So here the array is represented as or the image rather, is represented as a two-dimensional array of pixels. And in order to blur the image, you have to change the value of each pixel to a particular weighted average of that pixel's value and the values of the pixels surrounding it. So what does this code do? Well, we have this function called blur, and it takes a 2D array, which is our image to blur, and a number of iterations, which are the number of times that we want to apply this blur procedure. So we allocate a new 2D array that's the same size as the one we have. And then we have this runStencil call. So here, like in the previous example, we have to import parallel accelerator and use ACC, and then there's runStencil, which is the other parallel accelerator specific feature here. So what is going on in runStencil? Well, we want to operate on our two arrays, the one that's the image and the other that's the newly allocated empty array. We have this expression that starts with do, and this is what Julia calls a do block. So it's basically a function that binds two variables, b and a, and it serves as the final argument to runStencil. So here b is the newly allocated buffer, and a is the original image. And what the code here does is it indexes into b and says, okay, at the index 0, 0 in b, we want to write into that pixel based on what's at index 0, 0, 0 in a, the original image, plus all the pixels that surround that one, according to these particular weights, which I didn't put all of on the slide here. And also it should be noted that 0, 0 is a relative index, meaning that we actually do this for every index in b. And finally, at the end, we return, and here we actually swap a and b. and we bound them as B and then A, but we're returning A comma B, so they'll go into the next iteration of the stencil and they'll be swapped around, kind of in a double buffering style, and so on for however many iterations that we want to do. And here's some performance results for that. So here, again, the leftmost column is the performance results for Parallel Accelerator running on 36 threads, again on a 36-core machine as before. But as you can see, just like before, even when we're running on just one thread, Parallel Accelerator gives you a speed up of about 15x from the plain Julia version. And running on 36 threads, we get more of a speed up, and this results in a total speed up of almost 400x over plain single-threaded Julia. All right, so let's talk about the compiler itself in a little more detail. So as I mentioned, the standard Julia compiler parses Julia's source code into the Julia AST, and then it transforms that to LLVM-IR and finally generates native assembly code, or LLVM does. And what we do that is we intercept that process at the level of the AST in Julia. And we introduce new AST nodes for the parallel patterns that I mentioned earlier. We do some optimizations, and finally we generate C++. And I mentioned earlier in the talk that we intercept this process, and we do so using code typed. So as most of you may know, there's this function called code type that you can call to get the AST of any function. And this is really convenient for us. We just call that function, and then we pass the result to the first phase of our compiler, which is called domain transformations. And the domain transformations phase produces the domain AST or domain IR, which is like Julia's AST, except that it replaces certain AST nodes with new nodes that we have for the parallel patterns that I talked about. And we call those domain nodes. And then there's what we call the parallel transformations phase, which replaces domain nodes with what we call par4 nodes, each of which represents one or more parallel nested for loops. And loop fusion also happens at that stage. And finally, we hand all this off to our code generation pass, cgen, which converts par4 nodes into OpenMP loops. All right, so I want to say a few words about why we decided to build this on top of Julia. Why Julia and not some other language? Well, OK, so first of all, it's open source, which of course makes understanding Julia internals a lot easier. It's also faster than many scientific computing languages to begin with. It has good support for array-style programming, which is what we're trying to target. It's under active development with a strong community, all of you, and the Julia team has been really helpful to us. So in fact, we've been working closely with them for a while, and we have meetings with them every 2 weeks where they have to listen to us complain about 0.5 not being out yet. And finally, there's one last reason, and this is also something that my Intel colleagues here have also touched on their talks. And this is really something that's near and dear to my heart, I guess just because I'm a sucker for self-hosting compilers. But it's that unlike with some other scientific computing languages, writing a compiler for Julia in Julia is something that's not out of the question. And well, why is that? Well, for one thing, Julia has decent facilities for programming in the large. But it's also that Julia has these nice introspection facilities that make it really easy to access and manipulate ASTs in the language. And if you can imagine what it would be like to write, say, a MATLAB compiler in MATLAB, and what a painful thing that would be, you'll appreciate the feasibility of writing a Julia compiler in Julia. It's really something special. And people like Stefan actually care about making Julia a good platform for compiler research. So how cool is that? So finally, some caveats. Every talk about research code has caveats. First, package load time. So this is something that's come up repeatedly this week. When you use Parallel Accelerator, the first time that you try to call an accelerated function, there will be a pause while Julia tries to compile the Parallel Accelerator compiler itself. And it's a pretty big package. It is a compiler after all, so that takes a while. There are ways to avoid this. If you've heard of the userimage.jl hack, we have something in Parallel Accelerator called the embed function. So you can call ParallelAccelerator.embed, and that's essentially the userimage.jl hack packaged up as a function that you can call. So that makes it a little easier. The other thing is, right now, Parallel Accelerator can only handle a limited subset of Julia language features and a limited subset of Julia's base library functions. So in other words, you can't just put an ACC annotation on an arbitrary Julia function and expect it to just go faster right out of the box. So the examples that are in this talk give an idea of what kinds of programs we can support currently, and for more, you can look at our GitHub repo where there's an examples directory. But if Parallel Accelerator can't compile something that's in an ACC annotated function, it'll just fall back to running the function under regular Julia, and it'll give you a warning saying that it couldn't accelerate the code. So your code will run regardless of whether Parallel Accelerator can speed it up. And so one reason why I should say that an ACC annotated function might fail to compile is that Parallel Accelerator tries to transitively compile every Julia function that's called by the ACC annotated function. So if that function makes several Julia library calls, and some of them are doing things that Parallel Accelerator can't handle, it's going to try to compile everything in that call chain, and if there's anything that it can't support, then it will fail to compile the original function. So when you try using Parallel Accelerator, I think it's a good idea to start by annotating small computational kernels with ACC rather than wrapping an entire program in ACC. And our documentation has more details on which Julia features we don't support and why. But I should also note that these problems should go away with the forthcoming native threading backend, which will come with 0.5. So we're looking forward to that. And so to wrap up, Parallel Accelerator is a combination library compiler approach to accelerating Julia programs that are written in array style. And we've implemented as a Julia package that you can try out today. And we're looking for more users. So right now we have a lot of benchmarks, but we want to do more case studies on real applications. So if you think that the code that you write would be amenable to parallelization with Parallel Accelerator, do let us know. And here's how you can contact me. So thank you.